All right, so we're going to finish up section 11.2, which is still on adding up all the numbers in a sequence, except the difference this time is going to be the numbers could go on forever. Right? So if a series or a sequence of numbers goes on forever, you obviously can't add them up by hand. There's too many. So we got to figure out a way to deal with adding up an infinite amount of numbers. Okay? And I'll show you how we do that. When the amount of numbers you're adding up stops, and there's only a certain amount of them, we call that finite. When the amount of numbers you're adding up goes on forever, that is infinite. So when you add up infinitely many numbers, it is possible that you get infinity, right? That they don't add up to anything. It just, the more you add, the bigger it gets. But there are some sequences that you can add up an infinite amount of numbers and you actually get an answer. Or you approach an answer. Okay? You get very, very close to a number, but you never reach it. And that's part of what we're going to figure out. When can you add up infinitely many numbers and get an answer? And then when can you add up infinitely many numbers and not get an answer? So in sigma notation, that's what it would look like to add up an infinite sequence. What in that notation, let's start with the sigma notation on the left. What in the sigma notation tells you that it's an infinite series?
Top of it?
Yeah, top of it. It tells you that you're starting at the first term and you're adding up infinitely many, you're never stopping. What tells you on the right that it goes on forever in the expanded notation?
The dot to dot after the end.
Yeah, the dot 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 at the end. We didn't have this yesterday. We had a dot 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 in the middle. That just meant first term, second term, third, fourth, fifth, and at some point you reach the end. And we skip the ones in the middle, writing them down. But the dot 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 at the end means it goes on forever. So as I said earlier, adding up an infinite amount of numbers by hand, you can't do it because it'll take a long time. There's infinitely many numbers to add up. So we're going to look at trying to do this a different way. What do we call something when we graph it? If you get very close to it, but you never reach it?
Asymptote.
An asymptote. So when we start out, we're going to think of adding numbers visually. Okay, we're going to make a graph, and we're going to notice that the sums are going to get very, very close to a value. Right? They're going to approach it, but they'll never reach it. So if we can figure out the horizontal line when we draw it, that our sums are approaching but never reaching, that's what infinitely many terms would add up to. Because that's the idea of an asymptote. As you continue forever in one direction, you just get closer and closer and closer to that value. In this case, that value is going to represent a sum, adding up an infinite amount of numbers. Okay, so we're going to try to find a horizontal line, like y equals 5, or 6, y equals some number. And that line will be a horizontal asymptote for our sequence of partial sums. So we're going to make a graph. Okay, so we found partial sums yesterday. We didn't make a picture of them. Okay, today, we will. When an infinite amount of numbers adds up to something, we say that it converges. Okay, that's the word. Right? It converges. So if something doesn't converge, then the opposite of that is diverge. If you add up infinitely many numbers and you tell me that it diverges, it means it's not adding up to anything. It's just getting bigger and bigger and bigger and bigger and bigger. It's not actually approaching a number. And the number that we're going to approach is s. S is going to be the sum. So we're going to graph it. We're going to try to figure out that horizontal asymptote from a picture. Let's try and see. in this one, you want to add up, starting at the first term and going to infinity. So we're adding up infinitely many numbers. And that is the formula that's generating the numbers we're going to add up. Okay, so I'm not going to write them all out, but I did write some of them. When you write a capital S and a 4 below it, what does S sub 4 mean?
Fourth number of sequence.
So it represents adding up something.
Oh yeah, the first, you add up the first four.
You add up the first 4. Well, we've got a formula from yesterday to do that. It was a sub 1 times 1 minus r to the n over, and then what was in the bottom? 1 minus r. Okay, so for s sub 4, that's going to be a 4. And what's the r value there?
K minus 1.
Common ratio.
R is the common ratio. It's what you're going to multiply by each time to get from one term to the next. If you don't see it, then we'll just have to write down a few terms and figure it out. But does anybody see what R is? 2, well, let's plug in 1. So let's find the first term in that sequence. If you plug in 1, what's 1 minus 1? 0. What's 1/3 to the 0 power? 1. And what's 1 times 2? 2. So this is the first term. That's what that's telling you. Okay, let's find the second term. So let's plug in.
So 1/3 is the common ratio?
Yeah, 1/3 is going to be the common ratio. Yep. Let's find the second term. And if the common ratio is 1/3, then this should come out to, if you multiply 2 times 1/3, you get 2/3. So let's see. If you plug in 2, what's 2 minus 1? 1. What's 1/3 to the first power? And then what's 1/3 times 2? 2/3. So each time you're multiplying by another 1/3. What's 1/3 of 2/3?
6.
So multiply the top by 1 and the bottom by 3. So 2
2 6. Or 2 9s.
2 ninths is your third term. And what would your fourth term be?
2 18s. Oh, you said by 3?
Yeah, you're multiplying by 1/3 each time.
2 27s.
2 27ths. Now, we can add those up by hand. There's only 4 of them, so let's see what they add up to. And then I'm going to add them up with the formula, and from now on, I'm just going to use the formula because I don't want to have to figure them all out like this every time. So we've got 2 plus 2/3 plus 2 ninths plus 2 27ths. Okay, it adds up to 2.9627. That's how many decimals we have. 2.96. No, actually, that would round up. So we'll just say 2.963. Okay. Now, if you plug in 1/3 as your R value, and you plug in 4 for your N value, and you do all that out, you get 2.96, which is exactly what I got doing it all by hand. Okay. So, any question on how we got the 2.96, either doing it manually or just using the formula? Okay, what would change in this formula if I want to add up the first 5 terms?
Then
Yeah, what would N be?
5.
5, yep, and I already did all that out. And if you add up the first 5 terms, you'd have one more over here. If you wanted to do it manually, you'd have to figure it out and then add it to all the other ones. But it does add up to 2.9877. And what would N change to if I wanted to do the first 6?
6.
It would change to 6. And then you'd have to figure out the one after that if you were doing it manually or just use the formula. So if you add up the first 6 terms, it adds up to 2.9959. What does it look like it's getting close to? 3, yeah. So if you were to add up infinitely many of these terms, it would add up, or would get very close to 3. And the reason why it's getting close to 3 is because each time the number that you're adding is only 1/3 as big as it was before. So because what you're adding is getting smaller and smaller and smaller each time, it starts to make less and less and less of a difference the further you go. Eventually, what you're adding is so small, it doesn't even make a difference anymore. Even if you go to infinity, it's infinitely small. Okay, any question on that? All right, so now if you think of that, in terms of a graph, let's visualize what we just did. So what I want to do is think about these as coordinates. Let's do n, an estimate. Let's make a table. So let's do 1, 2, 3, 4, 5, and 6. Some of these we'll have to figure out. If you add up the first term in, let's go back to this. There it is. If you add up the first term in this pattern, what does it add up to? 2. If you add up the first 2 terms, what's 2 plus 2/3? It's 2 2/3, which if you fix that as an improper fraction, it's 6 8/3. So you get 8/3. If you add up the first 3 terms, well, let's just use the calculator. 2 plus 2/3 plus 2/9. 2/3 plus 2/9. 2 plus 2/3 plus 2/9. Okay, let's start using decimals because we got to graph this. So let's call it 2.89. And then if you add up the first 4 terms, we already had that number up here, 2.96. If you add up the first 5 terms, you get 2.9877. If you add up the first 6 terms, you get 2.9959. Okay, let's graph that, and then I think we can already see it's getting close to 3. But if you can't, the picture is going to make it very obvious. All right. Just trying to make the grid bigger so we can see it. There we go. All right, so 1, 2. If you add up the first 1 term, it adds up to 2. The first 2 terms, 8/3, that's 2 1/3. That's about 2.5, a little over 2.5. So first 2 terms adds up to 2.5. First 3 terms adds up to 2.89. And the idea is as you do these dots, you should see them getting close to something. First 4 terms, just barely under 3. First 5 terms, 2.98. And first 6 terms, let's see, 2.99. Can everyone see how as you add more and more terms up, they're approaching this horizontal line? That was the idea. Right? So if you make a visual, and that table starts to approach something, and it levels, it's kind of like it's leveling off, that means that you have found the number that they add up to. You just have to figure out where that dotted line is. Okay? And in this case, it was at 3. Okay, but you can also see it from the table. Okay, I think I already did all this. Now, when you look at that graph, wherever it just went, would you connect those dots? What's that? No, because this dot represents adding up the first 1 term. This dot represents adding up the first 2. Can you add up the first 1.5 terms? No, it's like finishing in 1.5 place in a race. You finish first or you finish second. There's nothing in between the 2. So that's why these are dots, and I didn't connect them. Because there is nothing between adding up the first term and the second term. There's nothing there. Okay, so I did that. Okay, well, actually, I already did example 2. So find the sum using a graphical approach. That's what I just did in the picture. That was example 2. So remember, this is what value again? The 2?
A1.
Yep, that's always your first term. If you forget that it's your first term, it's not a big deal. Just plug in 1 for k and calculate it manually. You're always going to get 2. Well, or whatever number is circled. And what's this? That's always your r. Again, if you forget that, not a huge deal. You could figure out the first 2 terms and then work backwards to figure out r. But it's a lot easier to just remember that. Yeah, let's try this one. So find the sum. So let's use this formula. This formula will find the sum for us. We just have to fill in the appropriate values for our problem. A1, 1 minus r to the n, over 1 minus r. Okay. What's A1 in this one?
4.
Yep, and what's r?
3.
3. So what's happening to the numbers each time in this pattern? Since r is 3. They're getting bigger, right? When r was a third, what we were adding each time was getting smaller. So now the numbers you're adding each time are just getting bigger and bigger and bigger as you keep adding more numbers. So let's see what happens with this. So fill these values in. What we want to fill in for n, well, we're going to do a few values. We'll do the first 4, the first 5, and the first 6. And we'll start to look at a pattern. But I don't want to do this by hand. I'm going to use the calculator. Okay, so A1 is 4. R is 3. And in the bottom, it's 1 minus 3, which is how much?
2. Oh, sorry,
Negative 2. So let's plug this in on the calculator. Then we can just change this number to whatever we want, and we can add up the first 2, 3, 4, 5, however many we want to do. All right. So we just got to be careful when we type all that in. So we've got 4 times, and then I'm going to put another parenthesis. 1 minus 3, make sure you use x. You always have to use x as your variable. 1 minus 3 to the x. Okay, so that's the top. The bottom is negative 2. And then I'm going to close my outer parenthesis, so everything there gets multiplied by 4. All right. Now, what I like to do is let's write the first 2 terms, 3 terms manually, and then let's add them up. And then we'll compare it to this formula, which adds them up. And if we get the same thing, then we know we typed it in right. Let's just do the first 3. What's the first term in this sequence right here? 4. Yep. The second term, if you plug in 2, what's 2 minus 1? 1. What's 3 to the first? 3 times 4. So that's your second term. And your third term. 3 minus 1? 2. 3 squared? 9 times 4? 36. Now, let's write down this, which is what that formula is going to do automatically if we typed it in the right way. What do you get if you add up the first term in that pattern? 4. First two,
16.
16, and then the first three.
52.
36 and 16 gives you 52. Okay. Now, in theory, I've typed in this correct. So if it's right, I'm going to go to my table, and I should be able to get those same values. Right, if I add up the first one term, I get 4. First two terms, I get 16. And the first three terms should add up to 52. Yeah, so I typed it in the right way. So now I can add up as many terms as I want, and I don't have to figure them out and do it this way anymore. If I want to add up the first 25 terms, that's what they add up to. So what's happening is I continue to add more and more terms.
It's getting bigger.
It's just getting bigger. Okay? It's not like this is approaching a value. Okay? As you continue to add more and more terms, the number is just getting bigger and bigger and bigger. Does anybody remember the word I said earlier? If you try to add up an infinite amount of terms and it just gets bigger and bigger and it doesn't approach anything?
Deconverge.
The opposite of converge. It does begin with a D.
Diverge.
Diverge, yeah. So this particular sequence on the right, this diverges. And it diverges because of that number. This sequence converged, and it converged because of that number. Anybody have a guess about this number and what it has to be to make the sequence converge?
Fraction. Or less than.
It has to be less than 1, yeah. If it's less than 1, then what you're adding each time is going to get smaller and smaller and smaller. If it's bigger than 1, then what you're adding each time gets bigger and bigger and bigger, which means it approaches infinity. So in that last example, we could look at the graph, but I don't even think we need to. You can just look at the table. 4, 16, 52. And if you want to go in order, I mean, you could do 4. Now we're at 160, 484. These aren't approaching a value. They're just growing, and there's no sign of it stopping. It's just getting bigger and bigger each time. So this particular graph, the dots would not look like this. They wouldn't start to level off. They basically look like that. You just all of a sudden see the dots start to take off, right, and curve up very, very sharply. When that happens, we say that the sequence or the series is divergent, or it diverges. So if I ask you, determine if the following converges or diverges, all you have to do is look at that number right there. We're gonna write this down. So sometimes a sequence can converge, sometimes it can diverge. Let's look at these different values for R. Based on what we said, do you think example A would converge or diverge? I'm not going to graph it because we already talked about it.
Converge.
Yeah, this would converge. This is the kind of pattern where each number is 8/10 the size of the one before it. So if you had a number like 100, and then you add the next one would be 80. The next one after that would be 8/10 of 80, which is 64. The next one after that is 51.2. If you keep figuring out the terms, you're going to notice that the terms themselves are approaching 0. Okay, the further and further I go, the smaller and smaller they're getting. And eventually they start to get so small that if you add them all together, the ones at the end don't make a difference anymore because they're just getting smaller and smaller and smaller. Right? Each number is 8/10 the size of the one before it. How about B?
Converge.
Yeah, that would also converge.
Would you ever have a negative R value?
No. Nope. No negative R values.
0?
No. R is either going to be between 0 and 1, not including 0, or it's going to be bigger than 1. Yep, those are the only two cases. How about C? That's going to diverge. In C, it means you're multiplying each number by 1.1. Take a number, let's say that was your first term, and multiply it by 1.1. That's your second term, 110. Okay. Your third term is 121. So because the terms you're adding are getting bigger each time, when you add them up, they're not going to approach anything. They're going to diverge. Okay. So any question on the difference between converging and diverging? Okay. So from looking at that, I just kind of summarized what we just said. If, as long as the absolute value of r is less than 1, and again, I don't think you're ever going to have a negative, so basically as long as r is less than 1, it will converge. If r is bigger than 1, it will diverge. Now, we would like to have a formula for what it converges to. This is the formula for a finite series. Okay? If you want to figure out what the first 3, the first 4, the first 10, the first 200, you use a formula like this. If you want to figure out what infinitely many terms add up to, you might think that infinitely many is more complicated. It's actually simpler. To find out what infinitely many terms add up to, it's a1 over 1 minus r. That part's the same, like 1 minus r in the bottom, 1 minus r in the bottom, but the top part actually gets simplified. It's just a1. So that's the formula for figuring out what an infinite geometric sequence converges to.
What if r equals 1?
It won't equal 1 because then you'd divide by 0. That would be a problem.
So it can't equal 1.
No. R cannot equal 1. So r is either going to be bigger than 1 or smaller than 1, but not 1. Right, so let's try this formula on a problem we already know the answer to. And now, because we have that, we don't have to do this graph stuff anymore. We don't have to look at these dots and try to figure out are they getting close to something. Right? We don't even have to make a table and then look at that. Let's use the formula a1 over 1 minus r. Okay. Did this one converge?
No.
No. Actually, I don't even think I wrote this diverged. It's diverges. How about this one? Did this one converge?
Yeah.
Yeah. Let's try the formula. a1 over 1 minus r. So now I'm eliminating having to do all this stuff I did earlier by hand, and I'm just going to try the formula. What's the first term in this pattern? 2. Divided by, what was r? 1/3. What's 1 minus 1/3? 2/3. And when you divide by a fraction, you take the bottom, you flip, and you multiply. So that's 2. So I took the top, keep that the same, flip the bottom, and multiply. And what's going to happen right here? The 2's cancel out, and what do you get? 3. And that's exactly when we write out the. Oh, we just did it graphically, so I don't think we. Where did I thought we did it graphically? Oh, right here, yeah. So we did it. We did it with a table here, and we saw we were getting close to 3, and then we did it with a picture somewhere. There it is. And we saw we were getting close to 3. So now we don't need the picture. We don't need the table. We can just use that formula that I just showed you. Now that formula only applies when something converges. If you try to use it when something is diverging, you get an answer, but it doesn't mean anything. Okay, so when it converges, that means R has to be what?
Less than 1.
It's got to be less than 1. Yep. So we did all that. So I don't think there's anything there. Okay, let's try this one. Okay, so looking at that, is this one going to converge or diverge? Why is it going to converge? R is less than 1. As you continue to add more numbers in this sequence, how does the next number compare to the one before it? It'll be half as big. Yep. So each time you add a new number, it's half as big as the one before. Okay, so let's try this. Let's see what we get. What's A1? 5 over 1 minus R. R in this case we just said is a half. What's 1 minus a half? Half. And what do you get if you divide 5 by a half?
2.
Or how many times does 0.5 go into 5? 10 times. Yeah. So if you were to add up infinitely many numbers in that pattern, if you figured them all out, they would add up to 10. So it saves us a lot of time. We didn't have to make a graph. We didn't have to put it in on the calculator and make a table. We can just use that formula. So this formula is only used to find the sum of an infinite geometric sequence. That's what you use it for.
Only when it's converging. Right?
Only when it converges, yeah. If you had something like the sum from k equals 1 to infinity of 4 times 3 to the n minus 1, well, you can fill in 4 for A1. You can fill in 3 for R. You will get an answer, but it doesn't mean anything. It only applies when it converges, which means this value needs to be less than 1. Okay, so part 2, there wasn't really that much to finish. That was it. How about if we had one like this? Sum from k equals 1 to infinity of 3 times 1/4 to the n minus 1. Is that going to converge or diverge?
Converge.
Yep, that will converge. And let's figure out what it converges to. What would go in the top? 3. And what would go in the bottom?
3/4.
Well, yeah, 1 minus R. R is a quarter, but then 1 minus a quarter is 3/4. So it's 3 divided by 3/4. So what do we do with that 3/4? Flip it. Yep. So I flipped it, and I multiplied, and then what happens? 12/3, which is 4. That's what you would get if you add up infinitely many numbers in this pattern.
So we just don't even acknowledge the exponent. The n minus 1, we just don't.
Well, you would use the exponent if you wanted to actually start generating the terms to add up. This is allowing us to skip generating the terms and just add them up without even knowing what we're adding up. Okay. Let's try generating the first 4 terms, and let's just check it manually and see if we get a number like 3.999. Okay, something close to 4. Okay, what's the first term in this pattern? 3. And then second term, what's 2 minus 1? 1. What's 1/4 to the first power? And what's 1/4 times 3? 3/4. Okay. So first, second, let's do the third. What's 3 minus 1? 2. What's 1/4 to the second power? 1/4 times 1/4.
2/8.
1/16. And what's 1/16 times 3?
3/16.
3/16. And let's do the fourth term. What's 4 minus 1? 3. What's 1/4 cubed? Fourth times a fourth times a fourth. 1/64. And what's 1/64 times 3? 3/64. Let's add those up and let's see if they look like they're getting close to 4. Okay, so we've got, let's get out of that screen, 3, and we'll do plus 3/4 plus 3/16 plus 3/64. And this is just adding up the first 4, and it already adds up to 3.98. So what does it look like it's getting close to?
4.
Yeah, it's getting close to 4, and we were able to figure that out without having to generate these terms. That's the advantage of the formula. Okay. So one important thing to understand, though, is the sum of all these numbers is adding up to what? 4. How about the actual numbers we're adding themselves? What are these numbers getting closer to? 3 3/4, 3/16, 3/64.
0.
These numbers are getting closer and closer to 0. Okay, that's important to understand the difference. When something converges, the numbers you're actually adding together are getting closer and closer to 0. What they actually add up to, well, that's what the formula tells you. In this case, they actually add up to 4. And I will ask that kind of question on the test. So is there any question on what I just said? The terms are getting closer and closer to 0. The sum of the terms is getting closer and closer to 4. All right, so that'll be homework. It's not that many questions. You've got about 30 minutes. You can work on that now. I'll pause it here, and I'll put the list of topics that are going to be on the test. So if I write a topic and you want to know anything about it, now would be a really good time to ask me.